Now, let us start with chapter 2. And chapter 2 is about Newton's laws. If you look at the top of this page, you will see some block diagram. And this one tells you where we are coming from. You're coming from a place where you learned velocity, acceleration, and stuff like that. And where are we going to? We are going to learn about forces, Newton's laws, and then we go on to after the three laws, we do gravitation, a little bit of gravitation and tides. So that completes chapter 2. All right, so let's get into chapter 2. The main focus of this chapter is force. So what is force? Force is a push or a pull acting on a body. So if you push something like that or pull something like that, well, that's a force. So force is defined as a push or a pull. And you can see that being defined over here. And the unit of force is Newton, which I will explain later on. Well, other units have come and gone, tons, metric tons, ounces, dynes. So we don't use them. We use SI units, which is newtons. So what we learn from here is that force is a push or a pull. Now, what can a force do to an object? So forces can do what to an object? What it can do, it can move an object. In simple terms, move an object or stop an object. Or in other words, we can say change the velocity of an object. Change the velocity of an object. Or even can change the direction. So if a soccer ball is rolling this way, if you apply a force, you can actually make the ball go in a different direction. You don't have to change the velocity, but you can change the direction alone. So a force can move or stop an object, change the velocity of an object, change the direction of an object, can deform an object. It can change the shape, in other words. It can change the shape of an object. And what else can it do? It can actually cause rotation. So when you apply a force on an object, you are able to cause it to rotate, turn, like opening the door. So that's a rotating action. So it can cause rotation. Forces are required to cause rotation. Forces are required to do work. We'll see work in the next chapter, but it is required. Force is a necessary component of doing work or transfer energy. So forces can do all these things and something more. So that is what you should understand here as to what forces can do. And remember, force is a vector quantity. So going on to the next page. The next page basically tells you the different kinds of forces. So before we go to the different kinds of forces, forces can be contact forces and field forces. Now, what is typically a field force? What is a contact force? A contact force is a force which we say comes in because we make a physical contact. So if I touch this pen, then that is a contact because I'm touching it, so that's a contact force. Whereas field forces, no contact is necessary. No force, no contact is necessary. Without even a physical contact, you can actually make something move. And what are the different kinds of, what can be an example of no contact force? It's something like this. So you look at the piece of paper, and what I'm doing is I'm taking this pen and I'm rubbing it on my hair, and you can see what happens. See? That's a no contact force. I didn't make a contact, but it is jumping onto my mark pen. So there we go. So this is a no contact force, where there is no contact necessary. Now what are some of the examples of no contact force? Contact forces require contact. So anything that you push and pull and all that, that is a contact force. Field forces can be gravitational, can be electrical, can be magnetic. So these are all field forces. They exist even without a physical contact. So for example, the Earth and the Moon, or the force between the Moon and the Earth is just a field force. It's a gravitational force. Now, electrical forces, magnetic forces, they don't really require a contact, so we call them. So in other words, electromagnetic force. Now, if you microscopically look into contact forces, you will see that even contact forces are sort of field forces because they are all electromagnetic in nature. Like, for example, if I'm attempting to touch something, when I touch something, what we physically see as being, making a contact is not actually a contact because there are atoms here, there are atoms on my finger. So when I go close to that, the atoms will start pushing against each other because what's surrounding those atoms are electrons. So those electrons will repel and it will create a force which stops my finger. So what is actually happening is, although we say this is a contact, microscopically it is not a contact. So when I touch somewhere, I'm not really touching, I'm just going close to it. It may seem funny because you'll say, all right, I'm just going to touch here, but no, I didn't touch. So I just went close. Well, when you go close, the force of interaction between my finger and here, the electromagnetic force of interaction, is what transfers the force to the other hand. So when someone slaps somebody, they didn't really touch that person. Microscopically, they didn't touch the person, they just went close, and the force got transmitted. So it seems a little funny anyway, but for all practical purposes, what we consider as contact force is a force that we see with our eyes. So for example, if I'm standing like that on the ground is pushing me up. Now that's a contact force. That happened because I am touching the ground, so the ground is pushing me up. So that's called a contact force. Okay? So field forces are forces which don't require a contact. Now if you look at it here, this page describes weight as a force. Now this weight is a gravitational force, and it is normally abbreviated by the letter W. Friction. Now what exactly is friction? On a later page, you can see on this page it describes more about it. You can see that this is how surfaces are when you microscopically magnify two surfaces. We think these surfaces are smooth, but if you magnify them, they look like this. So what happens when they sit against each other? These things cling against each other, and as you rub one object over the other object, these hills and valleys that are seen, they get lodged into each other. So when you try to move it, the forces, you're trying to peel those atoms, and that creates an opposition because the atoms don't want to move, and so that creates friction. So frictional force is, in one way, an electromagnetic force also. Okay? So that's what you should understand over there. Now, friction can be two types. You can have a static friction where an object is acted on by a friction, but the object is not moving. So that is called static friction. And kinetic friction is when an object is on the move and it is experiencing friction. So that's kinetic friction. So you can have, so when you drive your car, the wind resistance, that's called fluid friction. So this book is now sitting here. If I push it and the book doesn't move, so I'm pushing this book but it is not moving, that means there's a static friction. But when I pushed it and it started going off, and that is because during that time there is a kinetic friction, friction in motion. So these are some of the elements which are mentioned over here. There are other forces such as tension, normally seen in cables, tension force, and so on. So that leads us to the first law of Newton. The first law of Newton is clearly described over here. What it says is this: when an object is not acted on by net external forces, it should stay in the same state, which means an object should stay at rest if the net force on it is zero from outside. So the word external means not internal. An example of an internal force is you're sitting inside your car and you push the dashboard in an attempt to move the car. Now that is not going to move the car. That becomes an internal force. So if you want to move the car, you have to be pushing it from the outside. So only an external force can push something. But then sometimes you may have two external forces and the net force is zero. So when the net force is zero, what can happen is that the object is not going to change its state of motion. The object will stay either at rest or it will keep moving with a constant velocity. That's an important term. So when the net external outside force is zero, it should stay either at rest or move with a constant velocity. So this is Newton's first law. It just simply says an object will stay in the same state of motion. Now, an example of net force equal to zero is shown here. Net force zero, somebody is pushing this one this way forward and backward. So the net force is zero. These are both external forces. So the net force is zero. What's happening over here? It's not moving. It's staying still. Now, when I keep this marker here, or when I keep this pen here, how many forces are acting on this pen? There are actually two forces acting on this pen. And the two forces are, so that is a pen. The two forces acting on the pen are, one is the weight of the pen downward, which basically is gravitational force, and the other force is the force of push from the floor on the pen. So these are two forces, and those two forces are equal and opposite. So imagine I'm standing here, and that is the ground on which I'm standing. How many forces acting on me? One is the weight acting downward, and the other is the push by the floor. This is called contact force. Now, what do you know about these two forces? They're both equal and opposite. So what's happening to the net force? Net force is zero. Net external force is zero. So that means the object should stay in the same state, and that's what I'm doing right now. So I am being acted on by no net force, so I stay still. I'm not moving. But you can also have a situation where the net force is zero and the object is still moving. like a raindrop. Raindrops are falling from a great height. But you should understand one thing: when the raindrop is falling with the velocity, there is air resistance acting on it upward. And this air resistance is exactly the same as the weight of the raindrop. So what happens is the net force is zero on the drop, but the drop is still falling, and that velocity will stay constant. And we call this constant velocity terminal velocity. Some other examples are parachute. A parachute is coming down with a constant velocity. How many forces are acting on it? Mainly two forces, upward and downward. The net force is zero, and that's why it's coming down with a constant terminal velocity. So that is what Newton's first law is trying to stress. And Newton's first law also leads us to the term inertia. Now, inertia is a tendency of a body to stay in the same state of motion. That means if it is at rest, it wants to stay at rest. So I can give you a typical example. If I have a ping pong ball and a bowling ball resting on a table, which of these two has a greater inertia? In other words, which one has a greater tendency to stay in the same state of motion? In other words, which one will want to stay at rest? If you said the bowling ball, then you're right. The bowling ball has more inertia. It has a greater tendency to stay where put. And the reason behind it is it's got more mass. So mass is inertia. So inertia is a measure of basically mass, or mass is a measure of inertia. Now, if I just blow on these two balls, just blow, the ping pong ball is going to fly away, whereas this one is going to stay there. So which means it has more tendency to stay where put. So the inertia of this one is too high. Or, for example, imagine somebody threw a ping pong ball at your face, and at the same time somebody is throwing a bowling ball at your face. Now, which one of these two is easier to stop? Which has a greater tendency to keep going? This one has a greater tendency to keep going, whereas this one is easier to stop. Why is it easier to stop? Because it has less inertia. So it is easier to stop, and this one is harder to stop. So the tendency of an object to keep going with the same velocity, that is basically what is known as inertia. And you can see many of these examples, like for example, look at this, look at the pen. The pen is sitting here. When I pull this paper out quickly, the pen stays exactly in the same spot. Again, the paper is with me. I'm actually going to pull this paper. So when I pull the paper, the pen stays exactly there. Why? Because it has inertia and it has a tendency to stay in the same state. And you can see that example, this sort of situation in a bus. For example, when you're standing in a bus and the bus goes forward, what happens there? The bus goes forward, your body falls backward. Because your body has inertia, it wants to stay in the same state of motion, which means it wants to stay at rest. So with respect to the bus's floor, you are actually coming back. And vice versa. When you're moving forward, you have inertia, which means if the bus comes to a halt, then you are pushed forward. And that's one of the reasons why we wear seatbelts. And understand one thing, when your car is moving at 60 to 70 miles per hour, your body is moving at that speed. Your body is moving at 60 to 70 miles per hour. And if at all, God forbid, there is a crash, and when two cars come and hit, the car is literally going to come to a halt. Whereas your body, there's nothing to stop your body from coming to a halt. So therefore, your body will continue to go with the 60 or 70 miles per hour. That's what causes all the damage. So seat belts are a big help there. So wearing a seat belt is very essential, because when you're going, you're moving with the inertia, you're moving with the tendency to keep going. So we need some outside forces to kind of stop us. So that is the concept of inertia. And inertia is explained over here somewhere, probably on some other page. The inertia is explained here. There it is on page 55. So that is Newton's first law, which is connected to inertia. And here is inertia there. So inertia is a tendency of an object to. Now what we do is, let's go to the third law. Let me explain to you the third law. Now, third law is a law that says every force comes in pairs. Third law's main concept is every force comes in pairs. Forces come in pairs. So there's always, like, no force comes alone. If one force comes into existence, the other force immediately comes into existence, a pair. Now, the problem is always in identifying the pair. So which one is the actual pair of a force? That is kind of hard to say. For example, look at this. This is the weight acting on me, and this is the contact force. This is a weight acting on me, and that's a contact force. Now, if I ask you, where is a pair for the weight? What would be your answer? Where is a pair? There are only two forces acting on me. This is the weight acting on me, and this is the contact force acting on me. And if my question is, where is a pair for the weight? What would you answer? If you thought that this is a pair, then that is not right. So what is the problem over there? The problem is you're not able to identify the actual pair of the weight. Like, for example, imagine you're walking into a park and you see a bench, and on the bench there are two people. There's a male and a female. So there's a male and a female sitting on a bench. And if I ask you, where's the wife of this male? Can you jump to a conclusion and say the female is the wife? Not possible. You have to go through some conditions before you jump to this conclusion. So if you said this female is the wife of this male, just because you jump to the conclusion, I may have to tell you, all right, maybe the male is 92-year-old and the female is 2-year-old. And then you'll say, no, okay, so if they have to be pairs, they must be equal. That at least equal. So that means the husband and wife must be approximately same age. That's what I mean. And they are opposites. And then, well, if I say, okay, they are equal and they are opposites, they're both of the same age, can you jump to the conclusion and say that this one is the wife of this? Possibly not. Again, what if this male is a 25-year-old guy and the female is a 25-year-old tortoise or some other animal? So that again is wrong. So what is the condition required? They must be of the same kind. They must be both humans. So they must be of same kind. And the other, so okay, if they are equal in age, and if they are opposites, and if they are both humans, can you still conclude that this is the wife of this? Not possible, because they may be just twins. So it is possible that they're not. And what is the other condition required? They must have got married at the same time. Isn't it so? If they were really husband and wife, they must have got married at the same time. So here, they act at the same time. And they also act in the same line of action. and they must be acting on different objects. If all these conditions are satisfied, then only you can conclude that this and this are pairs. So let's come to the example again. The example I said is, here is I am standing here. So the weight is acting downward, and this is a contact force upward. Now my question was, where is a pair for this? Now we know that we have to go through the checklist. So let's go through the checklist. Are these two equal? Yes, that's true. Are these two opposites? Yes, that's also true. Are these two of the same kind? No, because this one is gravitational. That's a gravitational force, and this is a contact force. These are two different kinds. And when I say same kind, if one is electrical, the other has to be electrical. If one is magnetic, the other has to be magnetic. But then in this case, one is gravitational, the other is contact. So these are not pairs. Are they acting at the same time? It looks like that, but no. This one is acting because I'm making the contact with the ground. This has been acting from the time I was born. So it is not acting at the same time. Probably the same line of action. And acting on different bodies, are these two acting on different bodies? No. These are both acting on me. So these are not pairs. So a lot of these things are not true in this case. So we can clearly say that these are not pairs. So let's see that then which one is an actual pair. To understand the real pairs, you have to go down and assume that this is the Earth, not to scale. That is the Earth, and it's not to scale. What is weight? Weight is a gravitational force on me by Earth. Now, what is a contact force? It's a contact force on me by ground. So to find the pair is very easy. All you do is just change this word and this word, flip it. So that will get you gravitational force on Earth by me, which is basically going to be acting here. So this is a gravitational force on Earth by me. And these are the pairs. This one and this one are pairs. Now look at the conditions. Equal. Yes, they are equal. Opposites. Yes, they are opposites. Of the same kind. Yeah, both are gravitational. Act at the same time. Yes, they are. Act in the same line of action. You can see the line of action is the same. Acting on different bodies. Yes, this is acting on me and this is acting on the Earth. So these are the real pairs, not these. Now this one has its own pair. Where is a pair? Contact force on me by ground. Flip these. So contact force on ground by me, which is here. So this contact force on ground by me. So this is the pair. So this one's pair is here and this one's pair is here. So that's basically the essence of Newton's third law. Everyone thinks that Newton's third law is for every action there is an equal and opposite reaction. There's much more in meaning to it. So what it says is this: when a force is applied on the wall, there's a force applied on the person, and these two forces are exactly the same. So I am being pulled down with 800 newtons. So how much is the force I'm applying on the Earth? 800 newtons. It's the same force. Newton's third law pair. These are called Newton's third law pair, and they are the same forces. So let's say if Mike Tyson punches me on my face. If Mike Tyson punched me on my face, I can just laugh it off. You know why? Because if he applied a force on my face, let's say 1,000 newtons, I applied 1,000 newtons back on his hands. So it is a give and take. So he pushed me with 1,000, I pushed him back with 1,000. That's it. They're both pairs. So I can laugh it off, but maybe I have to cry later on because my face will be severely damaged. So who's going to be affected? That is something else. Like for example here, if I jump out of a building then this 800 Newton is the force with which the earth is pulling me down. And what am I doing in return? I'm pulling the earth up with 800 Newtons. Now, who is going to be affected? Is the earth going to be falling to me, or I'm going to fall to the earth? Naturally, I'm going to be affected because I'm light. I don't have much inertia, so I start moving, whereas this one stays where put. So that is inertia. So third law, Newton's third law's main concept is, for every action there is an equal and opposite reaction. And this is what you should understand when we talk about, say for example, rockets. So what is powering the rocket? How is the rocket going up? So rocket is pushing the exhaust gases down. So when the exhaust gases are pushed down, rocket is applying a force on the gases, and the gases will apply a force on the rocket up. Imagine you're swimming. How do you swim forward? What is the force that takes you forward? The force that takes you forward is because you push the water backward. When you push the water backward, the water will in turn push you forward. So that takes you forward. So you can see in many cases in airplane jets. So when there's a push backward, there's a push forward. Helicopter. What is happening in a helicopter? The blades of the helicopter, they are, so helicopter, the helicopter blades, what is it doing? It's pushing the air down. So what will the air do to the blades? They'll push it up. So that's what carries the helicopter. So, so Newton's third law is, you can see in different forms it's coming here. So let's say, for example, imagine there's a truck and a car. There's a car and a truck. Bad car. A car and a truck both collide. So they both come and hit each other and collide. So if the truck and a car collide with each other, who's offering a greater force? Truck on the car or car on the truck? Which force is greater? If you said the truck is offering greater force on the car, think again. Newton's third law says action and reaction are equal and opposite. So the force the truck offers on the car is the same as the car offers on the truck. So understand that concept. In other words, we cannot apply a force larger than what you get back. If I take this piece of paper and if I just flick it like that, how much force am I applying on this paper? The same thing as what the paper is applying on me. So there is no difference, and that is basically the third law's concept. And you can see the third law explained in those pages. Now let's go to the second law. So the second law. Oops, here it is. All right, so the second law is kind of opposite of what the first law is trying to say. Remember again, the first law says when there is no outside forces coming in, the first law says when there is no outside forces involved, when the net external force is zero, the object should stay in the same state of motion. And what Newton's second law says is when there is an external unbalanced force coming in, then the object should accelerate. The object will accelerate when there is a net force. So if you have an object like this, and if there is a force this way, 10 newtons, and there is a force backward, 10 newtons, this is net force 0. So no acceleration, no change of velocity, same state of motion. Whereas imagine this situation where you have a force of 10 newtons and there's a force backward of only 6 newtons. Is a net force 0? In this case, the net force is not 0, so it's going to have an acceleration. What if the force forward is 50 newtons and the force backward is 20 newtons? The net force is now 30 newtons, is much larger than the 4 newtons, and therefore the acceleration is going to be huge. So acceleration depends on the net force. So that is what the second law states. So what the second law states is the net force is proportional to the acceleration. the net force is proportional to the acceleration. And so if you write net force, and it also depends on the mass. So F is equal to ma. M must be in kilograms and A must be in meters per second square. So the unit of force is kilogram meters per second square, but in order to honor Newton and his contributions, we just put it as N. So we call it newtons. So force is measured in newtons. See that example over here? When a mass of 2000 kilograms is pushed with and it is accelerating at 4 meters per second square, what is the net force acting on it? Net force is 2000 times 4, which is 8000. And this picture also tells you the same thing. When one dog is pulling with F, this is going to accelerate with A. When this is pulling with 3F, it's going to accelerate more. So understand those concepts. So if you have one object of a certain mass, when you apply a small force, it's going to accelerate a small amount. If the same object is applied with a larger force, it's going to accelerate a larger acceleration. It's like you take this is the box, you push the box gently, then you have a small acceleration. You pull the box or push the box with a larger force, stronger force, then acceleration is going to be more. Or you can also consider this. You have a mass, you apply a certain force, and this will create a certain acceleration. And suppose the same force is applied on a bigger mass, the same force, watch the length of the arrow. Same force is applied on a bigger mass, what do you think is going to happen? It's going to have a small acceleration. It's like, imagine a bicycle and a car. If you push a bicycle with a force, it's going to accelerate some. If you push the same way, if you push a car, it's going to accelerate by a little bit. So this is something that you can understand. So if the mass increases and the pushing force is the same, you cannot expect a big acceleration. So it's like, imagine you are driving your car alone, so the mass of the car is small, and you push the accelerator, you're going to have a good pickup. You're going to have a good acceleration. But imagine there are 5-6 people sitting in your car, and if you try to push the same way, you're going to have a very poor pickup because the acceleration is going to be slow. So when your car is light, you can take off faster. So this is something that the second law tells us. The whole idea of second law is F is equal to ma. F is equal to ma. So wherever there is, F is equal to ma concept. Now here is another numerical. Here is a numerical. Now over here it says, an automobile manufacturer decides to build a car that can accelerate from 0 to 60 miles per hour in 10 seconds. In metric units, it's from 0 to 27 meters per second. The car's mass is 1,000. What's the force required? So now this is a two-stage problem. First, you have to find the acceleration, which is final velocity minus initial velocity over the time. And you got 2.7 meters per second square. And then what you do is you apply F is equal to ma, Newton's second law, and then you get the answer, 2,700 newtons. And over here it tells you that force of gravity, which is what we call as a weight. So weight is a force due to gravity. Weight is equal to mass times gravity. And it is just like force is equal to mass times acceleration. We call this acceleration due to gravity. We call this acceleration due to gravity. So you can see that this follows the same way. So F is a force, m is the inertia, and acceleration is there. So this is the equation that we use to describe weight of an object, and that's what is described here. And then on this page it tells you about centripetal force and centripetal acceleration. You already know that centripetal acceleration is v squared over r. When an object goes in a curved path, the centripetal acceleration is v squared over r. So what is the centripetal force? The centripetal force ma, you put this a over here, so you get F is equal to mv squared over r. And this is an important equation for problem solving, and here is an example of that. And you can see the example. When this car is taking a turn, the turn radius is 20 meters and is going at 10 meters per second. The equation is mv squared over r. Plug it in and get the answer of 5,000 newtons. And that is the centripetal force, and the centripetal force is towards the center of the circular path. We discussed that last time. Now you can see what's happening over here. When an object is tossed up, the object is moving up, but the acceleration is downward. And over here, the object is still moving up and the acceleration is downward. Over here, the velocity becomes 0 at the very top, but the acceleration is still there. The acceleration is still there. And then in the next diagram, you can see that this object is coming back. So you can see the direction of the velocity is downward and the acceleration is also downward. And why is it so? Because the weight is acting downward. So the actual acceleration is going to be always in the downward direction. Acceleration is always going to be in the downward direction. Now, over here it describes projectile motion. So you can see how the water jumps off from a water fountain. That's called projectile motion. Now, what is a projectile motion? Suppose you have a table. And suppose I drop something from the tabletop. So it falls straight down. Or imagine I just push this object sideways. It drops there. Which one do you think takes more time to fall? This one takes more time to fall, or this one takes more time to fall? If you said this one takes more time to fall, then you're not right. And if you said this one takes more time to fall, then you're not right also. So this is also, so what's the answer? The answer is they both take the same time. The reason? What is pulling this object down is gravity. Same way, this is also being pulled down by gravity. The only difference between this and this is this one is coming straight down and somebody pushed it horizontally. So it is continuously moving horizontally while it's coming downward. And so we have this. The object is going to land at the same time. So when you toss a football, the football's trajectory is this. So what happens is the velocity of the football, you give it this way. So you're giving a velocity like this, which has two components. When it climbs up a little bit, the velocity upward drops, but this one stays the same. Then the velocity drops further, this one stays the same. The velocity is 0 here, and this one stays the same. And then it starts coming down, and the horizontal stays the same. And then it comes faster, and the horizontal stays the same. And it comes faster than that, and the horizontal. So you can see what's happening to the vertical velocity. The vertical velocity is reducing, and then changing directions. It's all because the weight is pulling it down. Acceleration due to gravity is downward. That is the reason why it is happening this way. Why is the horizontal velocity not changing much? It's because there is nothing that is opposing it other than air resistance. We'll be talking about air resistance soon. And then there is something called simple harmonic motion. Now, simple harmonic motion is a motion that moves up and down. And when there is a movement that is up and down, the forces are sometimes upward and sometimes downward, so the acceleration also goes according to it. So when this object is stretched too much, then the force is upward. When the object is compressed here, the force is downward. So the forces and accelerations, they keep changing directions in simple harmonic motion. Now here is typically what happens when something is falling with air resistance. When something is falling in the presence of air resistance, this is what happens. What is air resistance? Air resistance is the opposition by the air. And when will that come in? It comes in when the objects try to move. Now, if the object is not moving, then there's no air resistance. Look at the coconut. The coconut is dropped by the monkey. As soon as it's dropped, it's not moving, so there's no air resistance. But it has got a weight, and so the net force is the weight. After some time, what happens? It is picking up a certain velocity, therefore there is an air resistance. Because there is an air resistance upward and the weight is downward, the net force is reduced. You can see the net force is smaller. After some more time, it's moving faster still. Now the frictional force is increased. The net force has come down. After some more time, it's moving with a high speed. When it's moving with a certain speed, the frictional force has built itself up to the same value as the weight. So what is the net force here? The net force is 0. The net force comes out 0. Now when the net force comes out 0, according to first law, what happens? According to first law, when the net force is 0, the object can either be at rest or move with a constant velocity. In this case, it's going to move with a constant velocity. And that constant velocity is what we call as a terminal velocity. So you can see this graph clearly. This is the velocity time graph. The slope of this graph is supposed to be the acceleration. So the slope is high and positive. That's 9.8. And then it reduces to 8, 7, 6, 5, 4, 3, 2, 1, 0. So the acceleration is 0 over here, because the velocity is not changing anymore. And that constant velocity is called terminal velocity. I hope things are getting clear. That's called terminal velocity. Now let's go through the universal law of gravitation. And this is on page 70 from this textbook. So what we need to understand in universal law of gravitation is that any mass attracts any other mass with a force. Any mass will attract any other mass with a force. And that force is proportional to the product of mass 1 and mass 2 and is inversely proportional to the square of the distance between the two. Now the distance between the two is taken from center to center of the two masses. The capital G is a universal gravitational constant, and it has got a certain value, 6.67 10 power minus 11. Numericals based on this will not be part of your requirement. Now over here you can see the same thing, the law of gravitation stated. You can see F is proportional to the m1 m2 over d square, and what this implies is that if m1 changes or if m2 changes, then the force is going to be dependent on these. So as you can see here in this diagram, the smaller object and a normal object, the force between them is F. Now when this one doubles in mass, you can see the force between them is also kind of doubled. So if m1 is changed and m2 is changed, then F will depend on both of them. D square is in the denominator, so if anything happens to the distance, the force is going to be changed accordingly. So you can see over here, if for example the distance between them gets doubled, so if the distance between them, for example, this is one object and this is the other object, and if the distance between them is just doubled, when the distance is doubled, 2d appears in the denominator instead of d. So 2d the whole square is 4d square. So the 4d square, the factor of 4, clearly indicates that the force is reduced 4 times. So the new force is 4 times smaller. Now if this distance is tripled, then the force is going to be reduced by 9 times, because 3d the whole square is 9d square. So when the distance between them is changed, the force changes in the inverse square proportion. So again, if the distance is doubled, the new force is F over 4. If the distance is tripled, then the new force is going to be F over 9. If the new distance is 4 times bigger, the new force is going to be 16 times smaller. So that's something that you need to understand in terms of proportion. And here's a typical example. You can see this person who weighs 160 pounds is standing on the earth, and the radius of the earth, the distance from this man to the center of the earth, is 4,000 miles. Now, this diagram is not to scale because the person is pretty tall then. So it's 160 pounds. It's okay to use pounds for comparison. Now, what will happen if this person, instead of distancing by 4,000 miles, if the person is standing on a 4,000 mile tower, which makes the total distance to the center 8,000 miles? What will happen if the distance between this person and the earth is doubled from 4,000 to 8,000? So when the distance is doubled, the force will become 4 times smaller, as I said just now. So therefore, the force becomes 160 divided by 4, which is 40 pounds. So this is, and now what will happen if the tower is 8,000 miles, making the total distance 12,000 miles, which will be like 3 times the distance, which means the force is supposed to be reducing 9 times. So this is the information that you need to know on this thing. What comes after that is orbital motion. Just to understand what is orbital motion, a simple way of understanding orbital motion is this. This is the floor. If I'm standing here and if I drop a marker, the marker will drop straight down. If I throw a marker horizontally, it will go down and fall here. If I throw it faster, then it will go and fall here. If I throw it still faster, it will go and fall here. If I throw it still faster, it will go and fall here. So how far it lands depends on how fast I'm going to project it. But why is it that it is going down all the time? It's because gravity is the only force that is pulling it down. So that's why as it is moving forward, it is also coming down. So technically, the time taken for this to come down here and this one to come down here is the same, because it is always falling. So in all cases, it's falling. The only difference is when you push it horizontally, it is moving to the right as it is falling down. And therefore, the time taken for it to fall is exactly the same. Now, if you look at it on a larger scale, now that's the Earth. And if you're standing on a tower or something like that, again, not to scale, if you do the same thing, if I throw a marker or something like that from here, it'll fall there. If I throw it faster, it'll fall here. If I throw it still faster, it'll fall here. If I throw it still faster, it's going to fall here. If I throw it still faster, it's going to fall here. If I throw it still faster, it's going to fall here. And if I throw it just at the right speed, it'll keep falling, 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 and it'll keep going round and round. That is called orbital motion. Now, what is happening to the object? It is falling, but the Earth is curved at the same rate at which it is falling, and so therefore it won't reach the Earth. It'll keep orbiting round and round, and the speed required for this is pretty high. It's something like 5 miles per second. And so if a satellite is to be put into orbit close to the Earth's surface, you need a speed of at least 5 miles per second to be given to that satellite. And then the satellite will orbit and keep going. There are thousands of satellites around the Earth doing multiple things like monitoring weather radars and weather satellites and spy satellites and natural resources satellites. So many satellites are there. They just go around faster and faster and faster. So that's an orbital motion. Now, when an object is going in orbit, when a satellite is going in orbit, how many forces are acting on it? It is just one force. It's a force of gravity, which is basically weight. When only one force is acting on the object, we call this weightlessness. When only one force is acting on the object, it's called weightlessness. So when we fall somewhere, when we fall from some height, if there's nothing opposing our fall and we are falling with the help of gravity, we will experience the weightlessness concept. So this is pretty much exactly showing you the different ideas of orbits. The next concept you need to know is tides. The last concept you need to know is tides. What's a tide? You can just do a little reading from here, but the most important message that you need to know over here is what causes tides. It is the moon. The moon's pull on the earth is what causes the tides. So as you can see here, the moon is pulling the earth in this direction, and therefore you can see here, when the water is being pulled from this side, then it becomes low tide here, and over here it's high tide. So all these tidal effects, they're all caused by the gravitational force of the moon. So this is pretty much what you need to know in this chapter, and at this time you should be in a position to go ahead and answer the questions in the quizzes. And here are some of the questions that you can actually go over for your better understanding. And so this one covers the whole Newton's laws. So you should be in a position to answer the questions which are in the quiz 2. So you should be able to go with quiz 2 and complete it. And we will be starting with our next chapter, which is energy and conservation of energy. And that will be put forth in the next video. All right. Good luck with chapter 2.